Hello viewers, my name is Ticha. This is a mathematics learning video. I'll be taking you through the topic Indices and Logarithms. This is a Form 2 topic. I'll show you the formulas that you need to apply in this topic, and as well as solving examples for you. And then I'll give you an exercise for you to try out whether you have understood or not. After that, I'll also be able to provide the answers which will guide you whether you have understood what we have covered, and much more. You are welcome to watch other topics that I have produced. So you are very much welcome. So in this topic, we are going to run indices and logarithms. The content of this topic are: number 1, indices; number 2, rows of indices; number 3, powers of 10 and common logarithms; number 4, logarithms of positive numbers less than 1; number 5, applications of logarithm. So I hope you are going to enjoy the topic. A good teacher is like a candle. It consumes itself to light the way for others. So we are going to look at what are indices. This may look like it's a new term, but if you are in secondary school, you have already used what is referred to as indices. We all know what is 3 to power 5. What it infers is 3 multiplied by 3 multiplied by 3 multiplied by 3 multiplied by 3. That is 5. 3 multiplied by itself 5 times. So we refer to 5 as power. We refer to 5 as power. And we read this as 3 to power 5. Actually, index is another word for power. So 5 can also be referred to as index. So here we can read 3 to power 5, which is the same as 3 index 5. When we have 2, 3 index, that is in plural, we refer to them as indices. So indices is plural of index. Let's take an example. We may have 2 to power 4, 3 to power 6, 4 to power 2, and 5 to power 3. So here we have now what we refer to as index. So we can say 4, 6, 2, and 3 are indices. The other number, we have 2, we have 3, we have 4, and 5. So 2, like 2 to power 4, this is index, and this number is referred to as base. So when they are more than 1, then we can say this is a base, this is a base, this is a base, and this is a base. So 2, 3, 4, and 5 can be referred to as, in plural, bases. So that is what is the meaning of the term indices. It is a plural of index, and index is the same as power. So like I had mentioned, it's something that you have dealt with in the past. Now we are going to look at the three rows of indices, and we are going to use examples to derive them. So we consider these three situations. So consider number 1. Suppose we have a cubed multiplied by a squared. So we can write this a cubed is the same as a multiplied by a multiplied by a. Then a squared is the same as a multiplied by a. So in total, if we count 1, 2, 3, 4, 5, it is equals to a to index 5. We take another scenario. We say number 2. Let's have a to power 7, a to power 7 divided by a to power 4. So we can write this a to power 7, can write a multiplied by 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 a 7 times 1, 2, 3, 4, 5, 6, 7. All of this divided by a to power 4, which is a multiplied by a multiplied by a multiplied by a. Since a is common, we can divide a by a, get 1. Divide a by a, get 1. Divide a by a, we get 1. A divided by a, we get 1. So we will be left with 1, 2, 3. It is equals to a to power 3. Now we go to the third scenario, where we have a to power 3 into bracket squared. So this is equals to a cubed multiplied by a cubed, which we can write a cubed is the same as a multiplied by a multiplied by a. Then the other a cubed, you also multiply a by itself 3 times a times a. So if we count 1, 2, 3, 4, 5, 6, it is equals to a to power 6. Now, from the 3 examples we have used, we can see, or we can derive the 3 rows of indices. Let's start with the first one. If you look at 3 and 2, when we are multiplying, when you add 3 multiplied by 3 plus 2, you get 5. You get 5, which is the final index in this case. Therefore, we can conclude the first row of indices, when the base is common, we can write it in short and write a to power 3 multiplied by a to power 2. Instead of writing it in expanding it, it is the same as a. Then we add the indices, which will give us a to power 5. From this, we can derive the first row of indices and say, if we have a to power m multiplied by a to power n, it is equals to a m plus n. So that is the first row of indices. The first row of indices. So we go to the second one. In the second one, you can observe 7. and 4. Here we are dividing. When you subtract 4 from 7, you get 3. So we can write it like this. The second row of indices, we have a to power 7 divided by a to power 4, which has given us the result a to power 3. So we derive the second row of indices, which is, if we have a to power m and we are dividing with a to power n, it is equals to a m minus n. So that is the second row of indices. Now we go to the third one. The third one, we have a to power 3 into bracket squared. You see, when we multiply 2 times 3, we get 6. Therefore, we can say a to power 3 into bracket squared is giving us a to power 6. And therefore, the third row of indices is a to power m into bracket to power n is the same as a to power m multiplied by n. So this is the first row, or the first row of indices, the second row of indices, and the third row of indices. So we are going to look at a few examples, but before we go to that, there's something we need to note. So the three rows of indices are, the first one, a to power m multiplied by a to power n is equals to a to power m plus n. The second row of indices, a to power m divided by a to power n is equals to a to power m minus n. And finally, the third row of indices, a to power m into bracket to power n is equals to a to power m multiplied by n. So after using these three rows for some time, you will be able to understand them and be able to apply when they are needed to be applied to solve a certain problem. Now that we know the three rows of indices, these rows, it is important to note that these rows are only applicable when the base is common or is the same. For example, if we have 2 to power 4 multiplied by 2 to index 2, then 2 is the base, and therefore we should be able to apply the first row of indices, which will give us 2, 4 plus 2, it is equals to 2 to power 6. But if we have a row, if we have an expression like 2 to power 4 multiplied by 3 to power 2, because the two bases are different, we cannot apply the rows of indices. So here you cannot apply the rows of indices, but you can do it here. So note that. So before we learn what is zero index, I have a good quote that I like. It says, give a man a fish and you feed him for a day. Teach a man to fish and you feed him for a lifetime. This quote is from a person known as Maimonides. The zero index. Maybe you have heard people say that anything to power 0 is 1. Anything to power 0 is 1. That is the zero index statement. Anything to power 0 is 1 and can be illustrated using the second row of indices. Let's take an example. Suppose we have a to power m. We divide by a to power m. The second row of indices tell us that then this is the same as m, a to power m minus m. And since m is common, this is the same as a to power 0, since m minus m is equals to 0. On the other hand, we can say that we can express this expression in another way and say a to power m divided by a to power m is the same as a to power m divided by a to power m. A to power m divided by a to power m, we get it is equals to 1. Now, since we are expressing the same statement, then it means that this is the same statement. Then it means a to power 0 must be the same as equals to 1. And therefore, this is what we refer to as a 0 index, that a to power 0 is equals to 1. And from this, we say that 10 to power 0 is equals to 1, 1,000 to power 0 is equals to 1, 1,000,000 to power 0 is equals to 1. Now that we have learned the rows of indices, I'm going to do 2 examples, but later on we will do more, just to demonstrate how we use the 3 rows of indices. Now, we are told to evaluate a to power 8 multiplied by a to power 2. So in this case, because it involves multiplication, we are going to apply the first row of indices. And this row states that a to power m multiplied by a to power n is equals to a m plus n. And therefore, our equation here, or our statement here, we can write it like this: a to power 8 multiplied by a to power 2. Since they have a common base, then this can be written as a 8 plus 2, which will give us a to power 10. We come to part B of this example. We are told we divide 4 to power 4 divided by 2 to power 2. We cannot apply any row of indices because the base are different, but still we can manage to divide. So this is 4 multiplied by 4 multiplied by 4 multiplied by 4 divided by 2 multiplied by 2. So this 2 divided by 4 is 2. We divide 2 by 2, we get 1. So we have 4 cubed, which is equals to 64. So note here that we have used the wrong method because we cannot apply any row of indices. Part C, we can apply the third row of indices, that states that a to power m into bracket to power m to power n, not m, is equals to a to power m multiplied by n. You don't have to write the row all the time, but just doing that so that you be able to follow. But once you understand, you just need to apply directly. So we have 3 to power 2 multiplied by, or to power 3. This is equals to 3 2 multiplied by 3, which is equals to 3 to power 6. So that's how you work out that problem. Example 2 we have, for x, we have 3 to power 2x into bracket to power 2 is equals to 81. For us to be able to get the value of x, we apply the third row of indices in the left side of our equation here. So we have 2x multiplied by 2 is equals to. On the right hand side, we write 81 in powers of 3 so that we have a common base, which is 3 to power 4. Simplifying here, we have 3 to power 4x is equals to 3 to power 4. Now you note that the powers or the indices are the same. 4x and 4 have a common base. Therefore, we can equate the indices and say 4x is the same as 4. Divide both sides by 4. Divide by 4. 4 divided by 4 is 1. 4 divided by 4 is 1. And therefore, our x is equals to 1. And if you substitute, you find 2 times 1 is 2 into bracket squared. That will be 3 to power 4, which is the same as 81. Come to the second question. We do the same. We open the bracket by applying the third row of indices. So we have 3x multiplied by 2 is equals to 496 is the same as 2 to power 12. You can find that using a calculator or mathematical tables. Now this, when you multiply, you get 2 to power 6x is equals to 2 to power 12. Now that we have a common base, which is 2, we can equate the indices and say 6x is the same as 12. Divide both sides by 6. Divide by 6. So 6 divided by 6 is 1. 12 divided by 6 is 2. So we have our x is equals to 2. So that is how you work out such a problem. Welcome to this lesson. This is the second lesson in the topic Indices and Logarithms. So you are much welcome. So in this section, we are going to learn about the negative indices. A negative indices is written like this: a to power minus m is equals to 1 divided by a to power m. Now we can prove that by using the indices and say that we have, let's say you call it a proof. Let's say we have a to power minus m multiplied by a to power m, which we know if we apply the first row of indices, this is the same as a to power 0. But a to power 0 is equals to 1. We know that. We have proved that in our earlier session. So we can say, then we can conclude that a to power minus m multiplied by a to power m is equals to 1, because it is the same as a to power 0. Therefore, we can write a to power minus m, divide both sides by a to power m, then you have a to power m. So that is a negative index. Again, we can do that practically and see whether it works like that. So let's say practically, let's have 3 to power 2 divided by 3 to power 4. So we can do this, can write this as 3 multiplied by 3, that is 3 squared, divided by 3, multiplied by 3, multiplied by 3, multiplied by 3, that is 3 to power 4. We divide 3 by 3, we get 1. Divide 3 by 3, we get 1. So we can conclude that this is equals to 1 divided by 3 squared. If we apply the rules of indices, we can say the same expression, 3 squared divided by 3 to power 4 is equals to 3 to power 2 minus 4, which will give us 3 to power minus 2. But we are working on the same expression. This one, and the same as this one. Therefore, their final conclusion should be the same, so that is the same as that. And therefore, this is what we call negative index. 3 to power minus 2 is equals to 1 over 3 squared. Alternatively, you can also write 3 to power 2 is the same as 1 over 3 to power minus 2. So that is what we refer to as negative index. We are going to see an example to see how it works. So in this example, we are told to simplify 25 squared into bracket index minus a half. So like we have said about negative index, we can write this as this. And so we write 25 squared into bracket to power minus a half is the same as, because a half here is negative, it is 1 divided by 25 squared into bracket. Now this changes to positive, so we have to power a half. Now this is equals to 1 divided by, in the denominator we apply the third row of indices, so we write this is 25, then we multiply 2 multiplied by 1 over 2, 2 divided by 2 we get 1, so it implies this is equals to 1 over 25. So our expression here, 25 squared to power minus a half, is the same as 1 divided by 25 by applying the negative index. So in this section we are going to look at fractional indices. So fractional indices are in fraction form and in simplified form. For example, this is a fractional indices, which is a to power p over q. In this case, p and q should not have a common factor. Example, it should be a number like a half, and not 2 over 6, because this can be simplified further to a third. At the same time, q should not be 0, because when you divide a number by 0, it is undefined. Or rather, we can use a simpler language. A 0 does not divide a number. It is undefined. Now, let's have a look at an example. Sometimes we talk of if a squared is equals to b, what this implies is that a, we get the square root for both sides. A is the square root of b. We don't put 2 here because that is the lowest root, but no problem. It's just like we don't divide a number by 1, because when you divide it by 1, it is always the same number. So this is called a is the square root. A is the square root of b. Again, we can say that a cubed is equals to b. Then what this means is that a is equals to the cube root of b. Here we put 3. So this is the cube root of a is the cube root of 3. We look at 4. A to power 4 is equals to b. Then what it means is that a is equals to the fourth root of b. So it can continue like that on and on and on. Practical example that we can take a practical example and say if 2 is equals to the square root of 4. What this means is that 4 is equals to the square root of 4 is equals to 4 to power a half. Then we can apply the third row of indices and say this is equals to 2 squared into bracket a half, which is equals to 2 multiplied by a half, and that should give us 2. So we can say the square root represent the fractional indices. So I hope that one is clear. We'll look at another example after this. Again, we say that the cube root of 27 is equals to 3. The indices can help us to prove that. So if we write in fraction form, we write 27 to power a third should actually be equals to 27 can be written in factors of 3. So 27 is the same as 3 to power 3, then into bracket a third. We apply the third row of indices, so we write 3, open the bracket, it is 3 multiplied by a third. So 3 divided by 3, we get 1. So this is equals to 3. So indices help us to prove the cubes of numbers. So another example, simplify 512 raised to power a third multiplied by 8 raised to power 2 thirds divided by 2 to power 4. So let's try and get a common base. So 512 can be written as 2 to power 9 or raised to power a third multiplied by 8 is the same as 2 to power 3 or raised to power 2 over 3 divide by 2 to power 4. Now here we can apply the third law of indices. We say this is 2, 9 multiplied by a third, multiplied by the same case here, 2, we have 3 multiplied by 2 over 3, divide by 2 to power 4. So we now have a common base. 9 divided by 3 is 3. 3 divided by 3 is 1. 3 divided by 3, you get 1. So we now have this, you have 2 to power 3, multiply by this, you only have 2 here, so 2 squared, divide by 2 to power 4. Now we can apply the first row of indices here. So we say this is 2, 3 plus 2 divide by 2 to power 4. So this will give us 2 to power 5 divide by 2 to power 4. We apply the second row of indices. We have 2, this is equals to 2, 5 minus 4, which finally gives us 2. So the simplification of this expression is equals to 2. This is another example. Simplify 12 x raised to power 5, y raised to power 3, and 4 x raised to power 3 multiplied by y. So we can write 12 x raised to power 5, y raised to power 3, all this is divided by 4 x raised to power 3 and y. First we can divide 12 by 4, you get 3. 4 divided by 4 is 1. Then we can write this is equals to 3 x to power 5, y to power 3, divide by x to power 3, y to power 1. Now here we can apply the second row of indices. We take now that we have x is a common base, so we can combine that. So we can write this is 3. We can start with x, then it will be 5 minus 3. Then we have y, which is 3 and 1. Here we have 1. Then it will be 3 minus 1. Minus because it is division. So this gives us 3. 5 minus 3 is 2. And 3 minus 1 is 2. So we have y squared. So that is how you simplify that. Another example, solve the equation 2 raised to power 2x into bracket raised to power 4 is equals to 256. So here we can apply the third row of indices and say this is the same as 2x multiplied by 4 is equals to 256 is the same as 2 to power 8, and therefore this will give us 2x times 4 will be 8x is equals to 2 to power 8. Now we have a common base, and if the two sides are equal, then we can say that the indices 8x is equals to 8. So 8x is equals to 8. We divide both sides by 8. Divide both sides by 8. So 8 divided by 8 is equals to 1. 8 divided by 8 is equals to 1. And therefore our x is equals to 1. And if you substitute here, 2 times 1 is 2. 2 times 4 is 8, which is equals to 256. That is the answer. The answer to that, the value of x. So you have 5 questions. With what we have covered so far, you should be able to do the questions. The questions are also available on YouTube, so you can visit Ticha Mtaa on YouTube. You can subscribe and be able to get the questions so that you will be able to do them. The answers are also provided on my YouTube channel, so you'll be able to see how you solve these questions. So hi there, in this lesson we are going to learn what is logarithm. Then later you'll be able to do some exercises and see whether you have understood. Welcome. To start our lesson, we start by looking at what do we call the logarithms or logarithm. Now consider the powers of 2. We can write 2 to power 0, we know it is equals to 1 from our previous lesson. 2 to power 1 is equals to 2. 2 squared is equals to 4. We have 2 cubed is equals to 8. We have 2 to power 4 is equals to 16. 2 to power 5 is equals to 32, and we can continue on and on and on. Now we notice that here we have what we learned as indices. So 0, 1, 2, 3, 4 and 5 are the indices. Now from there we'll be able to define what is logarithm. Therefore we say that logarithm indices 0, 1, 2 and 3, 4 and 5 are called logarithm of corresponding numbers to base 2. So this statement may not make a lot of sense for now if you have not dealt with logarithms earlier, but in a short while, after we do a few examples, you will be able to understand what actually logarithms are. But note that here we are talking of plural logarithms, which we are referring to as index. So for example, 0, the index, is a logarithm of 1 to base 2. So let us now look at how do we write the logarithm. For example, we take 2 squared is equals to 4. So we write the logarithm of 4 to base 2 is 2. Another example, we write, let's take 2 to power 5 is equals to 32. The log of 32 to base 2 is 5. So note the logarithm of 4 to base 2. The logarithm of 4 is this one. To base 2 is 2. So note that the logarithm of 32 to base 2 is 5. So when we write this in short form, this is how we write. The first one we say the log of 4 to base 2 is equals to 2, and the other one we say the log of 32 to base 2 is equals to 5. So note, when we write numbers in this form, that is 2 to power 0, 2 to power 1, on and on, we refer to that form as index form. So that is index form. So this one, when we write in logarithms, we say this is logarithmic. Logarithmic form. Now, if you look at this, we can be able to change from logarithmic form to index form. Note here that we can identify this because 2 to power 2 is equals to 4. Also, 2 to power 5 is equals to 32. So we can convert from the logarithmic form to index form, and that is what we are going to do. So we are going to use the information on the table shown here to convert from index form to logarithmic form and from logarithmic form to index form. For example, the first one, we are given in form of index form, that is 3 squared is equals to 9. The logarithmic form of this is, note here, 3 squared is equals to 9. So we can use that format. So here, 3 cubed is equals to 27 can be written as the logarithm of log of 27 to base 3 is equals to 3. This one we are told in index form 3 to power 4 is equals to 81. So we can write log of 81 to base 3 is equals to 4. So note here that the index is what we are calling the logarithm of the number. Here we have been given logarithmic form, and therefore we are supposed to write the index form. So note here that 2 to power 6 is equals to 64. So we write 2 to power 4 is equals to 64. This one you say the logarithm of 25 to base 5 is equals to 2. And finally, the logarithm of 36 to base 6 is 2. So we write logarithm of 36 to base 6 is equals to 2. So that is how we convert from index form to logarithmic form and from logarithmic form to index form. So I hope you have followed how we have done that, because we are going to do more on that. Copy? In general, we can say from what we have worked out the missing part of this table, then if we are given a to power m is equals to n, then we can write the logarithmic form of this is the logarithm of n to base a is equals to m. In this case, this is the index form, and this is logarithmic form. So you can now be able to convert from one form to the other using the same logic that we have followed in this example. So having done that, I'm going to do for you two examples so that you can see how we can apply this knowledge. Then after that, I'll give you an exercise which you can try out. So in our example 1, write in logarithmic form, we have a. So these expressions are in index form, and to write them in logarithmic form, this is how we write. Start with a. So we say the log of 64 to base 4 is equals to 3. So we write logarithm of 64 to base 4 is equals to 3. Then we go to part B. We are told that 27 to power a third is equals to 3. So we say the logarithm of 3 to base 27 is a third. So we write it like logarithm of 3 to base 27 is equals to a third. Finally, we have C, where we are told x power y is equals to k. So the logarithm of k to base x is equals to y. So logarithm of k to base x is equals to y. So that is how we convert this expression to logarithmic form. We go to example 2. So in example 2, we are given expressions in logarithmic form to write in index form. So I'll start with a. We are given log of 100 to base 10 is equals to 2. Now in index form, you say 10 to power 2 is equals to 100. So this is equals to 10 to power 2 is equals to 100. So that is in index form. Part B, we are told the log of 128 to base 2 is equals to 7. In this case, you say 2 to power 7 is equals to 128. So 2 to power 7 is equals to 128. And finally C we are given log of k to base z is equals to g. So in this case, you say z to power g is equals to k. So z to power g is equals to k. So that is how you convert from index form from logarithmic form to index form. So from there, I'm going to give you an exercise which you can try out and see whether you have understood all about logarithms. So in this exercise, you have two questions. The first one, you will need to write this expression in index form. Then we have number 2. Question number 2, you write the expressions in logarithmic form. That is, from index form to logarithmic form. And that brings us to the end of this lesson. But check, there are a lot of things that I'll be posting in my YouTube channel related to the same topic, that is revision questions and other extra information that I may come across. So get answers for the given exercise from Ticha Mtaa YouTube channel. It is important you open a Gmail email account, like and subscribe Ticha Mtaa channel so that you get all the lessons and revision questions that I have prepared. If you don't know how to open a Gmail account, you can get assistance from Cyber. Or if you know how to browse the internet, you can just go to www.google.com. Then you find an option of opening an email account. If you don't have one, you can use one. If you are a student, use your parents' account. You will be able to access these materials. Hi there. This lesson is on logarithms. So by the end of the lesson, you should be able to read the logarithm of a number from our logarithm tables, which are found in the mathematical tables. So you are all welcome. So in this lesson, we start by looking at the standard form. Standard form is a scientific way of writing numbers. So we are going to consider a few examples and see how we write a number in standard form. For example, suppose we take 100. This can be written as, we take the decimal from the last point there, 2 point to the left, so we have 1.0. Multiply by 10, it's the same as 100. So 1.0 times 100 is the same as 100, which we can write as 1.0 multiplied by 10 to power 2. So now this is the standard number, the standard form of 100. Let's take another number. We take number 2. We have a number like 150. So just like we have done above in 100, we take the decimal point 2 decimal places to the right, and therefore we will have 1.5. The decimal will come there, multiply by, now this will be the same as 100, so it will be 10 squared. So that is a standard form. Another example is when we consider a number that is less than 1. For example, we go to Roman number 3, we have 0.5. How do we write 0.5 in standard form? 0.5 is the same as 5 divided by 10, which we can separate and say it is 5 multiplied by 1 over 10. Now 1 over 10 is the same as the inverse of 10. So we write 5 8.0 multiplied by 10 to power minus 1. Another number is 0.125. 0.125. So we have 0.125. This is the same as 1.25. Now in this case, when we have a number less than 1, we move the decimal to the right. So we move it one decimal place to the place in between 1 and 2. So we have 1.25 multiplied by, now when you move to the right, it is the same as 1 over 10. Remember, if you divide 1.25 by 10, you still get 0.125. So this is equals to 1.25 multiplied by 10 to power minus 1. So that is a standard form. Let's have our another number, our last number, which is 0. So we call this 5, 0.008. So to write this number in standard form, then we move this decimal point 3 decimal places to the right. So 1, 2, 3. So we have, it is equals to 8.0 multiplied by, we have moved the decimal place 3 places, so it is over 1,000. So this will give us 8.0 multiplied by 1 over 1,000 is the same as 10 to power minus 3. So that is how we write numbers in standard form. Now we are going to look at powers of 10 and common logarithms. Let's have a look at powers of 10. Powers of 10. So we can take 10 to power 0 is, we know it is equals to 1. 10 to power 1, we know it is the same as 10. 10 to power 2 is equals to 100. We have 10 index 3 is equals to 1,000. That is 10 times 10 times 10. We have 10 to power 4 is equals to 10,000. So we can continue like that and on, and you get the powers of 10. Now we have mentioned in our previous lessons that 0, that is 0, 1, 2, 3, 4, that is 0, 1, 2, 3, and 4 are called logarithms to base 10. Are called logarithms to base 10 of number 1, that is of 1, 10, 100, 1,000, and 10,000. Of we say 1, put a comma, 10, 100, 1,000, and finally 10,000. So this, and we remember we also refer to them as indices. So they are also called logarithms to base 10 of 1, number 1, 10, 100, 1,000, and 10,000. Now note here that they are logarithm when the base is 10. The base is 10. So we can have, as we have seen earlier, we can have different base. Then the logarithm will be of that particular base. Now when the base is 10, we can put that down. When the base is 10, 10, we sometimes we refer to this as common logarithms. We refer to this as common logarithm. In common logarithms, we sometimes leave the base. So in common logarithms, such that, so instead of writing logarithm of 1000 to base 10 is equals to 3, we write, when it is common logarithm, the log of 1000 is equals to 3. So when we don't indicate the base, it means we are dealing with common logarithm referring to as the base is 10. Otherwise, if the base is not 10, it is always indicated. For us to be able to get the common logarithm, we must be able to express a number to the powers of 10. E.g., suppose we want to get the logarithm of 50. 50, we should be able to write 50 to the powers of 10. So let's assume 50 is equals to 10 to power x. Now we can get the logarithm of 50 to base 10 is equals to x, as we have seen in our earlier lessons. Now, how do we get this x here? We know the logarithm of 10 to base 10 is equals to 1. We know the logarithm of 100 to base 10 is equals to 2. And now that 50 is in between 100 and 10, in between 100 and 10, then the logarithm of 50, which is x, should be greater than 1 but less than 2, since it lies in between 10 and 100. So we can do that by calculation. I will not show you the calculation for now, but we can be able to write 50 is equals to 10 to power 1.6990. So that is the number. That is how we can express 50 to the powers of 10. And therefore, we should be able to get the logarithm of 50. Now, the logarithm of 50 to base 10 is equals to 1.6990. So we have managed to get the logarithm of 50. If we want to get the logarithm of 80 to base 10, it is equals to 10, maybe we say to power y. So we will need to do the same calculation just like we have done with 50 to be able to get the value of y. And that will be a lot of work. So let's see how now the logarithm table helps us to find the common logarithms. It is tedious to do calculations every time we wish to express a number to the powers of 10, so as to get a common logarithm, like we have seen in our previous example. This is the point where we need logarithm tables to help us express any number to the powers of 10. For example, if we have x is equals to 10 to power y, then it is very easy. We can get the logarithm of x to base 10 is equals to y. So if we are able to express any number to the powers of 10, then it becomes easier for us to get the common logarithm. So we are going to look at the logarithm table, how we read the logarithm table, and how we use it to get the common logarithms. Now, this is a logarithm table. It is found in our mathematical tables, which in most cases it is a requirement. When you are reporting to high school, you are required to come with one. So we are first of all going to understand how do we read the logarithm table. So the logarithm table has separated into two tables. The table, this is the value that you need to express to the powers of 10. That is from 1.0, 1.1, on and on. It goes up to 9.9. So this is just a section of our logarithm table. From there we have this table starting from 0, 1, 0, 1, 2, 3, 4, up to 9. That is the main table. And then we have another table which has numbers 1, 2, up to 9. This is called the table of differences. So the logarithm table helps us to express a number to the powers of 10. You can see here it is logarithm to base 10. And therefore, we are able to read straight the expression of a number to the powers of 10 from the mathematical tables. Now, this is the column of the number. Remember, we did the standard form, so we also make use of that knowledge in getting the logarithm of numbers. Then we have columns. This column, you can see it has decimal places. It starts with the decimal places. But the other columns do not have decimal places. What implies that whatever format is in the second column, it is applied to all the other rows up to number 9 here. For example, this is it is supposed to be read as 0.2041, this one. Because it has a decimal point here, if we take a number like this one, it should be read as 0.2227. So that is how we read the numbers. Then this table of differences, we are going to see how we make use of that in getting the logarithm of numbers which has more than 3 significant figures. Remember, if you check your mathematical tables, it is written as 4-figure table on the cover. So meaning that we work with 4 figures. 4 figures, as you can see here, we have 4 figures. So when we have more than 4, we round off to the nearest so that we get 4 significant figures. So let's look at the logarithm of a number like 2. So 2, we can say logarithm of 2 to base 10 should be equals to, or rather, let's do it like this. Let's say 2 should be equals to 10 to power x. Now, instead of doing our calculation the way we have been doing, then we are able to get the 2 to the powers of 10. Let's say 2 power 2.0 is equals to 10. Now we come to the first column here. We move up to where we have 2. The number that is next to it, that is, this is 2.0, is 0.3010. So 2 is the same as 10 to power 0.3010. And therefore, the logarithm of 2 to base 10, or rather 2.0, which is the same as 2, is equals to 0.3010. 3010. So you can see now the logarithm table has made it easier for us to be able to get the logarithm of numbers to base 10. So remember, this is to base 10, and that is why we refer to it as common logarithm. Let's now take several examples and see how we get the logarithm of other numbers in other formats. So read the logarithm of A 1.57, B 2.452, C 21.4. So we start with A. So to read the logarithm of 1.57, it's like saying we express 1.57 to the powers of 10. So let's say it's to the power of x. So we need to find x. After getting x, we will be able to get the logarithm. So from the logarithm table, we go to the first column, that is the x column. We go down up to where we have 1.5, then move horizontally up to where the number that corresponds with 7, which is 0.1959. So this means that 1.57 is the same as 10 to power 0.1959, implying that the logarithm of 1.57 is equals to 0.1959. You can either indicate 10 or you leave it, because we are dealing with common logarithms. We now go to part B of our question. We are supposed to get the logarithm of 2.452. Now this is where the table of differences will come in. Remember, we have only dealt with 3 significant figure number. So 2.45, we say that we should be able to get its logarithm. Then we should be able to write 2.452 to the powers of 10. So let's say call it y. So y is the logarithm. Now we go to our first column. We read downwards up to where we have 2.4. Then we move across the horizontal up to where we the number that corresponds with 5, which is this one. So that is the number. So this means that 2.45 is equals to 10 to power 0.3892. But remember, here we have 2, which we need to take care of. Now the 2, we move to the table of differences. This is where we have 2. We read the number downwards that correspond with the row that we were. So this is 4. But now 4, we don't read it as 4. We read it as difference of 2 is 0.0004. Now we are going to add 0.042, so this is to 0.3892. So we add to 0.3892. So you get 6983 0 point. So we have now added, implying that 2.5, not 5 but 2.452 is equals to 10 to power 0.3896 to the powers of 10. So now we can be able to get the logarithm and say the logarithm of 2.452 is equals to 0.3896. So that is how you get the logarithm of a number that have 4 significant figures, and that is how you make use of the table of difference, which is this one. So we are going to look at part. So part C, we are required to get the logarithm of 21.1. So this is a number that is greater than 10. And our tables read up to 9.9. So we are supposed to express 21.4 to the powers of 10. Let's say we have 10 to power A. Now, for us to be able to do this, we have learned how to write a number in standard form. So 21.4 is the same as 2.14 multiplied by 10 to power 1. From there, we can be able to express 2.14 to the powers of 10. We come to our table and we read the values 2.14. So this is where we have 2.14. We move across up to here. We have 2.14 is this number here. So 0.3304, and therefore 21.4 is equals to 10 to power 0.3304 multiply by 10 to power 1. Now remember our first row of indices. When we have a common base, we can add the indices, and therefore 21.4 is equals to 10. When you add 0.3304, you add to 1, you get 1.3304, and therefore we can now get the logarithm of our number 21.4. So we say the logarithm of 21.4 is equals to 1.3304. So I hope now you can be able to get the logarithm of numbers, as I have shown you how to read the logarithm tables. Lastly but not the least, going to look at characteristic and mantissa, and I'm going to demonstrate that to you using this example. Find the logarithm of A 256 and 4,250,000. So we start with A. So 253 is more than 10, so we first of all express it in standard form. 253 is the same as 2.53 multiplied by 10 to power 2. So using the mathematical tables, we can now express 253 to the powers of 10. So we say this is 10. We read from the mathematical tables, the number is 0.4031 multiplied by 10 to power 2. So this is equals to the first row of indices allow us to add this. So we say it is 10 to power, this is 0.4031, you add to 2, you get 2.4031, and therefore the logarithm of 253 is equals to 2.4031. Now in our logarithm there, we have, this is a whole number 2, and this is a decimal number. So the whole number is referred to as a characteristic, and the decimal number is known as the mantissa. So this is a characteristic, the positive number here, and the mantissa is this one. This is referred to as mantissa. So in logarithm, that is characteristics and the mantissa. We go to part B of our question. So we go to B. We are supposed to get the logarithm of 4,250,000. So we can write this in standard form. So 4,250,000 is the same as 4.25 multiplied by 10. This is 1, 2, 3 at 1. That is 1, 2, 3, 4, 5, 6. 10 to power 6. That is, we move the decimal point from here 6 places to the left. Now we write, we can be able to express this 4.25 to the powers of 10. So this, from the logarithm table, we get this is 10 point, it is 0.6284. You multiply by 10 to power 6. Now we add the indices. This will give us 10. When you add 0.6284, you add to 6, you get 6.6284. So from here, we can now be able to get the logarithm of this number. The logarithm of 4,250,000 is equals to 6.6284. So again, we have the characteristics. This is the characteristics, and again we have our mantissa here. This is the mantissa. So that is the mantissa. So that brings us to the end of this lesson. So I hope you now understand how to get the logarithm of a number to base 10, that is common logarithm, and you'll be able to do that. So we are going to do an exercise now. So do this exercise. Follow the rules that I have shown you. Know how to read the logarithm tables, and this will be very useful in future as we are going to look at the application of logarithms. So get answers for the given exercise from Ticha Mtaa YouTube channel. It is important you open a Gmail email account, like and subscribe Ticha Mtaa channel so that you get all the lessons and revision questions that I have prepared. If you don't know how to open a Gmail account, you can get assistance from Cyber. Or if you know how to browse the internet, you can just go to www.google.com. Then you find an option of opening an email account. If you don't have one, you can use one. If you are a student, use your parents' account. You will be able to access these materials. Logarithm of positive numbers less than 1. Positive numbers less than 1 are decimal numbers. For example, we can take 0.023. We want to get the logarithm of this number. For us to be able to do that, we express 0.023 in standard form. So we say 0.023 is the same as 2.3. We move the decimal point 2 places to the right, and then we multiply by 10 to minus 2 because we have moved the decimal to the right. Now, using the logarithm tables, we can get the logarithm this 2.3. That is, we express 2.3 to the powers of 10, and using the tables, logarithm tables, we get it is 0.3617. Then we multiply by 10 to power minus 2. Now here we can say for us to get the logarithm, so we need to add minus 2 plus 0.3617. So this is a negative number, that is minus 2, and this is a positive number. So under normal circumstances, then we would say this plus this and we work out. But in logarithm, we don't do it like that. We write this is equals to 2 bar point 3617. What this means is that this is a negative and this is a positive value. So we are mixing a positive value, and a negative value. This is positive. So when you combine both, that is the logarithm. It is read as bar 2.3617. Let me write that for you. So it is read as bar 2.3617. The negative sign is written above 2 to emphasize that only the characteristic is negative. So we are going to do a few examples to see whether we have understood what we are talking about. In this example, we will find the logarithm of 0.68, part B 0.021, and part C 0.00029. So we start with A. What we need here is to express 0.68 to the powers of 10. So let's say 0.68 is equals to 10 to power x. So once we get x, we should be able to get the logarithm. So we write this in standard form. So 0.68 is equals to 6.8. Move the decimal point to the right one step. Multiply by now 10 to power minus 1. So using now the logarithm tables, this 6.8 is the same as 10 to power 0.8 325 multiply by 10 to power minus 1. So we add, we get, this is 10 to power, when you add, you get bar 1.8325. Remember what we have talked of the bar, that it is, the bar means only the characteristic is negative, the mantissa is positive. So now this is 0.68 to the powers of 10, implying the logarithm of 0.68 to base 10 is equals to bar 1.828, not 2 but rather 3, 8325. So that is the logarithm of that number. We go to part B. We are required to find the logarithm of 0.021, and this we follow the same steps. So we write 0.021 in standard form, which is 2.1 multiplied by 10 to power, now it is bar 2 or minus 2. So we using the logarithm tables, 2.1 is the same as 10 to power 0.3222 multiplied by 10 minus 2. So when you add these two, you get it is 10 bar 2.3222. So the logarithm of 0.021 is equals to bar 2.3222. So that is the logarithm. Finally, we go to C. Our C will get 0.009. So we express 0.00029 in standard form. So this is 0.00029 is equals to 2.9 multiplied by, the decimal will move four steps, so it is 10 to power minus 4. So this is equals to, from the tables, 2.9 is the same as 10 to power 0.46, 0.4624. You multiply by 10 to power minus 4. Then when you combine, you get this is 10 bar 4.4624. So the logarithm of, let's write it down here, the logarithm of 0.00029 is equals to bar 4.4624. So that is example, and I hope you have understood how now to get the logarithm of positive numbers less than 1. Now we look at anti-logarithm. Anti-logarithm is the reverse of getting the logarithm. So, for example, what is the number whose logarithm is 0.1752? So this is to mean that you are given the logarithm so that you find the number. So actually, we can say if our number is x, it is equals to 10 to power 0.1752. So we need to find the value of x. Now, after the logarithm table, in the mathematical table, we have another table known as anti-logarithm table, and that is the one that you use. The reading of the anti-logarithm table is similar to the way we learned how to read the logarithm table, so I will not repeat that. What I will do is from the logarithm table, go to the column labeled x and find the number that corresponds with 0.175. You find this number is 1.496. But remember, we want to get the anti-logarithm of 0.752. So we have a difference of 2. So this 2, we said we call it a difference. We will read it from the table of difference. To the difference of 2, you get it is 0.001. That is the table of difference. Then you are supposed to add the 2. So you get 7, you get 9, you get 4, you get 1. This means that the number with x is equals to 1.497. In this example, find the number whose logarithm is 2.2040, part B, by 3.3452. So we start with the part A. So what this means is that if we assume our number is x, it should be equals to 2.2040. Since we are saying that anti-logarithm is a reverse of getting the logarithm, we can separate this number such that we have 10 to power 2 multiplied by 10 to power 0.24. Let's write that properly. 0.2040. So we know that 10 squared is the same as 100. So that's 100 multiplied by, here we have anti-logarithm of 0.2040. We get it is 1.60, just like the way we have obtained the anti-logarithm. So when you multiply 100 by 1.60, you get that it is equivalent to 160. So 160, so our x is equals to 160. It is a number whose logarithm is 2.2040. So that's a correct value. You can confirm by getting the logarithm of 160. We go to part B of our question, by 3.3452. So what this means is that if our number is y, then y is equals to 10 to power by 3.3452. So this is equivalent. We can separate this and write this is 10 by 3 multiplied by 10 by 0.3452. So 10 to by 3 is equivalent to 1 over 1,000. Multiplied by the anti-logarithm of 0.3452 is actually 2.214, and therefore when you divide 2.214 by 1,000, you get it is 0.00214. So that is the number whose logarithm is given as this one. So our y is that. So that is how you work out such kind of a question. So sometimes we ask ourselves, where are we going to apply the knowledge that we sometimes go through? So it is important to understand that in everything that you do, there is application. Logarithms can be applied, but for now we look at application of logarithm in multiplication and division. So let's start with multiplication. So we use logarithm to multiply two numbers. So we have 126. We have 126 multiplied by 60. We can write this as 126 in terms of powers of 10 by using the logarithm. So we say it is 10 to power 2.1004. You multiply by 10 to power 1.7782. So this, we have used the logarithm table to be able to express 126 and 60 to the powers of 10. Now using the first row of indices, we can add because we have a common base. So when you add 2.1004 and 1.7782, you get 3.8786. Now we can again separate this and write this is 10 cubed multiplied by 10 to power 0.8786. So we get the anti-logarithm of this, and we will get that 10 cubed is the same as 1000 multiplied by the anti-logarithm of 0.8786 is 7.561561. So when you multiply by 1000, you get this is 7,561. So that is the product of 126 multiplied by 60. So we have applied the logarithm to multiply these two numbers. So division is another area where we apply the knowledge of logarithms. So we use logarithms to divide. For example, 9/6 divide by 12. Just like we have done with the multiplication, we write 9/6 powers of 10. So this will give us 10 to power 2.9713 divide by 12 to the powers of 10. We get 10 raised to power 1.0792. We can apply the second row of indices since it is division. So we subtract 10 with 2.9713. We subtract 1.0792. So when you subtract that, you get it is 10 raised to power 1.8921. We now get the anti-logarithm. We can separate this and say this is 10 to power 1 multiplied by 10 to power 0.8921. So this is 10 multiplied by the anti-logarithm of 0.8921 is 7.8. So when you multiply by 10, you get it is 78. You can try in using another method and find out whether when you divide 9/6 by 12, you get 78. Now we have talked of applications of logarithm, multiplication and division, but we can organize our work better than the way we have presented. So let's do these two questions again. For division, we arrange our work like this. We make a table whereby we have a column there and a column there and the last one. So this one, we write the number there. This SF stands for standard form, and this is the logarithm of the number. So for example, we have 126. When you write 126 in standard form, it is 1.26 multiplied by 10 squared. We can now be able to write this number in terms of logarithm in a better way, because we take 2, which represent 10 to power 2 when you add, and then we get the logarithm of 1.26, which gives us 1004. Then we go to 60. The standard form is 6.0 multiplied by 10 to power 1. So for 10, logarithm of 10 to power 1 is 1 point. The logarithm of 6 is 0.7. We have 782. And since it is a multiplication, we add the logarithm. So we put a line there. So when you add 4 plus 2 is 6, 0 plus 8 is 8, 0 plus 7 is 7, then 1 plus 7 is 8. We put a point there. 2 plus 1 is 3. So in standard form, then we go the reverse. 3 here represent 10 to power 3. Then we get the anti-logarithm of 0.8786, which will give us 7.561. So we can now multiply, and our final answer, now we write it here, it is 7561. That is 7,561. So the answer is 7,561. Now we come to division. So 936 divided by 12, we draw the similar table to the one that we have done with the division. So we have the number there. Our number is 936 and 12. Then we have standard form. So we have 936 is the same as 9.36 multiplied by 10 to power 2. Then we have 1.2 multiplied by 10 to power 1. So we now have the logarithm. So here we have the column for logarithm. Logarithm of 10 to power 2 is 2. Logarithm of 936 is 0.97. So we have 7, 1, 3. Logarithm of 10 to power 1 is 1. Logarithm of 1.2 is 0.0792. So we put a line there. We subtract because it is division. So when you subtract, you get 3 minus 2 is 1. This will have 11. 11 minus 9 is 2. Here we are left with 6. We borrow 1. 16 minus 7 is 9. So here we have 8 minus 0 is 8. 2 minus 1 is 1. Now in standard form, this 1 means it is 10 to power 1 multiplied by the anti-logarithm of 0.8921 is actually 7.80. Now our number is, you multiply 7.80 times 10, you get 78, just like we had obtained using the other method. So our answer is 78. So we take another example. 215 multiplied by 428 divided by 214. So we are going to make our table. So this is the number column. So our number are 215, 428. But note these two numbers we are multiplying, then we divide the product by 214. So you put a line there. So the standard form is 2.15 multiplied by 10 to power 2. This is 4.28 multiplied by 10 to power 2. So this is a standard form. Then we have the logarithm column. The logarithm of 10 to power 2 is 2. We check the logarithm of 2.15. We will get it is 3324. Then we have the logarithm of 10 to the power 2 is 2 point. The logarithm of 4.28, we get 6314. And because we are multiplying here, we add the logarithm. So 4 plus 4 is 8. 2 plus 1 is 3. 3 plus 3 is 6. 3 plus 6 is 9. Point. 2 plus 2 is 4. Now we are supposed to divide the product of this by 214, so we put 214 there. When you write it in standard form, it is 2.14 multiplied by 10 power 2. The logarithm of 10 to power 2 is 2 point. A logarithm of 2.14, we get it is 3304. Then here, because we are dividing, we subtract the logarithm. So 8 minus 4 is 4. 3 minus 0 is 3. 6 minus 3 is 3. 9 minus 3 is 6. Point. 4 minus 2 is 2. Now 2 represent 10 to power 2. And then we get the anti-logarithm of 0.6334, which we get it is 4.299. So when you multiply this, you get this is 429. So this is equals to 429 as the answer for that problem. Now in this example, we are told to evaluate 2.15 squared. Now we have been using the column of standard form. Once you get used to working these kind of problems, you cannot omit it. So let's find what is 2.15 squared. So using a table, we are going now to have only two columns. So we have the number and we have the logarithm column. So our number is 2.15 squared. Now the logarithm of 2.15 is 0.3324, and it is squared. So it's like we are supposed to say 0.3324, and then this is 10, then multiply by 10, 0.3324. So instead of that, we simply multiply this by 2. So we get the logarithm is 2 times 4 is 8. 2 times 2 is 4. 3 times 2 is 6. 3 times 2 is 6. And then 0 times 2 is 0. So our number is our logarithm is 0.6648. We get the anti-logarithm of this, and from the tables we get it is 4.622. So the answer to this, that is 2.15 squared, is 4.622. So another example, evaluate 4.21 cubed. So just draw a table where we have two columns. This is a column of the number, our number is 4.2. This is 0.21 cubed. So we get the logarithm of 4.21, which is 0.6243. Now because it is cubed, we just multiply by 3. So when you multiply by 3, you get 3 times 3 is 9. 4 times 3 is 12, so carry 1. 2 times 3 is 6, so we have 7. 6 times 3 is 18, so we have 8 and we carry 1, so 1.8. The anti-logarithm of this one, 1 represents 10 to power 1. We get the anti-logarithm of 0.8729, which gives us 7.4628. 4628. So the answer to this one is 74.628. That's how you work out that. So another example, evaluate. So just like we have done with the other examples, let's draw a table. So we have, this is for the number, this is for the logarithm. We have 525.3. Then we multiply by 0.0243. Now, the logarithm of this, first of all, we have 2, because we move the decimal 2 places to the left point. The logarithm of 5.253 is, we have 7.204. Then this one, you move the decimal point to the right, so you have bar 2. Then the logarithm of 2.43, you get 38. We get 5.6. So we put a line there. So we first of all add. So because of this multiplication, when you add, you get 4 plus 6 is 0. So we have 0 there. Then we have 5 plus 0 plus 5 is 5. We have 2 plus 8 is 0. Then carry 1. So 8 plus 3 is 1. So here we have 3. 3 plus bar 2, you get 1. It's like 3 minus 2. Higher. We have another number here, 115. Now 115, you get its logarithm. First of all, we have 2 because of the decimal point moving to the right, to the left. The logarithm of 1.15 is 2 point. That is not point, but 2. That is 0. It is 060607. So we put a line there. So because we are dividing, then we are supposed to subtract. So 0 minus 7, you get 3. We have borrowed 1 here. So this is 4. So this is 0. We borrow 1 here. 10. 10 minus 6 is 4. Then 0 minus 0 is 0. Point. This is 1 minus 2. So we have a minus. So it is bar 1. If it is bar 1, it means it is 10 to power minus 1. Then we get the anti-logarithm of 0.0443, which we get it is 1.1099. So this means you divide this number by 10 because of this minus. So the solution to that is 0.11099. That is the answer. So this is a simple one. We are supposed to add bar 1.24 plus bar 2.32. So we say that when we have the mantissa is a bar, it means this is negative and this is positive. So you just need to separate this and say bar 1.24 is the same as bar 1 plus 0.24. Then we have bar 2.32 is equals to bar 2 plus 0.32. So we have we now add, so this will be 6, 5, and then we have 0.0. So bar 1 plus bar 2, you get bar 3. So this is equals to bar 3.56. So that's how you work out that. So get answers for the given exercise from Ticha Mtaa YouTube channel. It is important you open a Gmail email account, like and subscribe Ticha Mtaa channel so that you get all the lessons and revision questions that I have prepared. If you don't know how to open a Gmail account, you can get assistance from Cyber. Or if you know how to browse the internet, you can just go to www.google.com. Then you find an option of opening an email account. If you don't have one, you can use one. If you are a student, use your parents' account. You will be able to access these materials. So in this lesson, we are going to look at what are roots. And roots here refers to like the cube root, the square root, the fourth root, and so on. So we are going to look at how we make use of the logarithm tables to be able to get the roots. For example, the square root of 16, we know it is 4. But now let's apply the logarithm tables to evaluate that. So we have 16. The square root of 16 is the same as 16 to power a half, which 16 we can write using logarithm table to the powers of 10. So we can say 16 is the same as 10 to power 1.2041, and then into bracket to power a half. Now, applying the third row of indices, we can open this bracket and say this is 10, 1.2041, and we multiply by a half, which will give us, this is equals to 10. When you divide by a half here, we cancel 2 by a half. It is 1. 2 divided by 2 is 1. Then here we have 0.602. This is 0, so we round off, we get 1 instead of 0.5. So we get 10 is equals to this is the same as 0.601. Using the mathematical tables, we get the anti-logarithm of 0.6021. We get it is 4.000, which is the same as 4. So we have seen that we can use the logarithm tables to get the square root of a number. This is going to help us where we want to get the square root of a number which doesn't have a perfect root, like 16. So another example, use logarithm table to evaluate the cube root of 27. We know cube root of 27 is 3, so we are going to use the mathematical tables to confirm that. So we have square root, this is cube root of 27 is equals to 27 to power a third, which we can write 27 to the powers of 10 using mathematical logarithm tables. So we write 27 is the same as 10 to power, check from the logarithm tables, it is 1.43144, then 14. All this into bracket, then we put a third. This is equals to, we open the bracket, it is 10, 1.43144, we multiply by a third. We multiply by a third, that is applying the third row of indices. So when you multiply there, we divide by 3, this number by 3, so we get 10 to power 0.4771. If you check from the logarithm table, the number whose logarithm is 0.4771 is equals to 3.000, which is the same as 3. So you can see Starting from what we know, we can, that is a cube root of 27 is 3, we can be able to use logarithm tables to get cube root of that number. So let's have another example. So we get the fourth root of 81. So we will say the fourth root of 81 is the same as 81 to power a quarter. So we express 81 to the powers of 10. So you get, this is 10 to power, we get it is 1.9085, all this into bracket to power a quarter. So we apply the third row of indices, so we say it is 10, 1.9085 multiplied by 1 over 4. So this will give you 10 to power 0.4771, which is equals to 3. So the fourth root of 81 is equals to 3. Now, this example, we want to get the square root of 529. So we have the square root of 529 is equals to, we write 529 to the powers of 10, which is 10 to power 2.7235. This is into bracket to power a half. So we open the bracket, we get, this is 10, 2.7235 multiplied by a half. So this will give you 10. When you divide 2.7235 by 2, you get it is 1.3618. Now we can separate this and write this is equals to 10 to power 1 multiplied by 10 to power 0.3618. Because when you apply the first row of indices, you come back to this to the previous step. Now from there, now we can say this is the same as 10 using the logarithm tables. We get the anti-logarithm of 0.3618. We get it is 2.3. So when you multiply 2.3 by 10, you get 23. So that is a square root of 529. So we are going to use a logarithm table to get the cube root of this number. So cube root of that number, we can write it like this. This is 2461, which now, just like we have dealt with the other examples, we write this to the powers of 10. Now when you get the logarithm of 2.461, you get it is 0.3911, and this is to power a third. So when you open the bracket, you get it is 10 to power 3.3911, and we are supposed to multiply by a third because it's a cube root. So when you multiply, you divide 3.3911 by 3, then you get it is equals to 10 to power 1.1304. Now in this case, now we can separate and say this is the same as 10 to power 1 multiplied by 10 to power 0.1304. Now we can write this is as 10 multiplied by, now the anti-logarithm of 0.1304 is 1.3502. So this is equals to, when you multiply by 10, then you get it is 13.502. So you can see now that we have managed to get the cube root of this number, which does not have a perfect cube root, and using the logarithm tables, it is possible you get the cube root of this number. So you can use the logarithm tables to get any root of a given number. So here we are supposed to get the square root of 0.125. So we can do it in another different way using a table this time. So we can say this is we make a table. This is the number, this is the log, then we want to get the cube root, the square root of 0.125. The logarithm of this number is, we can say bar 1 because it is less than 1, positive number less than 1. Bar 1, the logarithm of 1.25 is 0.0969, and because we are getting the square root, we are multiplying this by a half. So when you multiply that by a half, then you get that this number will give us problems because the characteristics is negative and the mantissa is positive. So we cannot combine this number. So in this case, what we do is we modify our number. For example, we can write bar 2 plus 1.0969. So realize that here we have added 1 to the mantissa and subtracted 1 here. So if you add bar 2 plus 1, you still end up with bar 1. So from there, we can now be able, because now we must have the characteristics must be a whole number. So we now have bar 2 plus 1.0969. This is divided by 2. So when you divide bar 2, otherwise we can write it like this. Now we write bar 2 divide by 2 plus, we separate the fraction, 1.0969 we divide by 2. So when you divide that by 2, you get here bar 1 plus this will be 0.5485 when you divide this by 2. And now we can combine and say this is equals to bar 1.5485 5. And what this means is that here we have 10 to power minus 1 represented by bar 1. Then we get the anti-logarithm of 0.5485, which is the same as 3.536. Now our final answer will be, it is equal, so you divide 0.536 by 10, you get it is 0.3536. so that is the square root of 0.125. So here we are supposed to get the square root of 0.125. So we can do it in another different way using a table this time. So we can say this is we make a table. This is the number, this is the log, then we want to get the cube root, the square root of 0.125. The logarithm of this number is we can say bar 1 because it is less than 1, positive number less than 1. Bar 1, the logarithm of 1.25 is 0.0969, and because we are getting the square root, we are multiplying this by a half. So when you multiply that by a half, then you get that this number will give us problems because the characteristics is negative and the mantissa is positive. So we cannot combine this number. So in this case, what we do is we modify our number. For example, we can write bar 2 plus 1.0969. So realize that here we have added 1 to the mantissa and subtracted 1 here. So if you add bar 2 plus 1, you still end up with bar 1. So from there, we can now be able, because now we must have the characteristics must be a whole number. So we now have bar 2 plus 1.0969. This is divided by 2. So when you divide bar 2, otherwise we can write it like this. Now we write bar 2 divide by 2 plus, we separate the fraction, 1.0969 we divide by 2. So when you divide that by 2, you get here bar 1 plus this will be 0.5485 when you divide this by 2. And now we can combine and say this is equals to bar 1.5485. And what this means is that here we have 10 to power minus 1 represented by bar 1. Then we get the anti-logarithm of 0.5485, which is the same as 3.536. Now our final answer will be, it is equal, so you divide 0.536 by 10, you get it is 0.3536. 0.36. So that is the square root of 0.125. So example 7, look at the cube root of 0.00315. We do that with the help of a table. So we make our table there. We have number, we have the logarithm. So our number is the cube root of 0.00315. Now the logarithm to this, you say it is by 3 because the decimal point will move 3 points to the left, to the right point. Logarithm of 3.15, we get it is 4,969. Then we multiply by a third because we are looking for the cube root. Now bar 3 is divisible by 3, so we will get it is bar 1. We get it is bar 1 point 04969 divided by 3, you get 1, get 6, you get 5, and you get 6. So we now get the anti-logarithm. Anti-logarithm, we get it is bar 1 represent 10 to power minus 1 multiplied by the anti-logarithm of 0.1656 is 1.464464. So when you multiply that by 10, you get your answer is 0.1464. So that is the cube root of this number. So in this example, we want to get the fourth root of 0.325. So we make a table to be able to do that. Here we have the number, and here we have the logarithm. From there we have the fourth root. So we have fourth root of 0.325. So this will be, the logarithm will be bar 1 point 5119 multiplied by 1 over 4 because we are looking for the fourth root. Now we cannot divide by 1 by 4, so we modify our number in such a way that we have bar 4 plus this will be 3, so that bar 4 plus 3 will give us bar 1.5119. You divide by 4. So note here we have not changed our number, but rather we have modified. So here it is bar 4 divided by 4 plus 3.5119. All this is divided by 4. So when you divide bar 4 by 4, then you get here it is bar 1 point. This you divide by 4, you get it is 8780. So when you get the anti-logarithm, bar 1 represent 10 to power minus 1 multiplied by anti-logarithm of 0.8780 is 7.551. So this is 7.551, and therefore our fourth root to this number is 0.751. 5, 5, 1. So that is a solution to that. So you can use the logarithm tables to get the roots of numbers, even 5, root 5, root 6, root 10, any other number that you would like to get its root. So get answers for the given exercise from Ticha Mtaa YouTube channel. It is important you open a Gmail email account, like and subscribe Ticha Mtaa channel so that you get all the lessons and revision questions that I have prepared. If you don't know how to open a Gmail account, you can get assistance from Cyber. Or if you know how to browse the internet, you can just go to www.google.com. Then you find an option of opening an email account. If you don't have one, you can use one. If you are a student, use your parents' account. You will be able to access these materials. So before we do several questions regarding or application of rows of indices, let's have a look at what are the three rows of indices. We have the first one. We are told if we are given a raised to power m multiplied by a raised to power n, it should be equals to a m plus n. The second one is if we are given a raised to power m divided by a raised to power n is equals to a n minus n. The third row of indices is if we are given a raised to power m into bracket raised to power n is equals to a m multiplied by n. So these are the three rows that we will be applying in the following questions or exercise that we are going to do. So in this question, we will apply the rows of indices. So first of all, let us write these terms in a common base. So we say 4 is the same as 2 raised to power 2 into bracket raised to power 5x, and then we divide by the other one. We open the bracket, so it is applying the third row of indices, 3x multiplied by 2, that will give us 6x. So it is 2 raised to power 6x, which is equals to 256 is the same as 2 raised to power 8. We open the brackets here, so we have 2 multiplied by 5x, that will be 2 to power 10x, divided by 2 to power 6x, which is equals to 2 to power 8. We combine this using the second row of indices, so this is the same as 2 10x minus 6x is equals to 2 to power 8. Now from there we can get now 10 minus 6x is the same as 4x. So 2 raised to power 4x is equals to 2 to power 8. Now since the base are the same, we now equate the indices. So we say 4x is equals to 8. We divide both sides by 4. Divide by 4. So when you divide 4 by 4, you get 1. You divide 8 by 4, you get 2. So our x is equals to 2. So that is the answer to that question. So in this question, we are supposed to solve for x. So we are given 81 to power 2x multiplied by 27 raised to power x all over divided by 9 raised to power x is equals to 729. So let's try to establish a common base so that we apply the rules of indices. So 81 is the same as 3 raised to power 4. All this is into bracket raised to power 2x multiplied by 27 is the same as 3 cubed. All this is raised to power x is equals to before we go to that, we find this is 9 is the same as 3 squared into bracket raised to power x. 729 is the same as 3 to power 6. Now we can open the brackets and say this is 4 times 2. We get it is 3 to power 8x multiplied by this will be 3 raised to 3x all over divided by 3 2x is equals to 3 to power 6. Now from there we can now use the first row of indices and the second row of indices, and we write this is equals to 3 to power 8x. We now add 3x and we subtract 2x, that is the second row of indices, is equals to 3 to power 6. Therefore we have 8x plus 3x that will give us 11x. 11x minus 2x that will give us 9x. So 3 to power 9 is equals to, that is to power 9x is equals to 3 to power 6. Now since we have established a common base, it means that the indices are the same. So we say 9x is equals to 6. Divide both sides by 9. So 9 divided by 9 will give 1. So the common factor here is 3. So 6 divided by 3 is 2. 9 divided by 3 is 3. So it implies that our x is equals to 2 over 3. And that is the answer to that question. So in this question, we are supposed to find x, whereby we are given that the 2 raised to power x minus 3. We are also given 8 raised to power x plus 4, which is equals to 64 divided by 2 raised to power x. So first of all, we established a common base so that the 2 can be written as 2 raised to power 5, then into bracket x minus 3 multiplied by 8 is the same as 2 cubed into bracket x minus plus 4 is equals to 64 is the same as 2 raised to power 6 divided by 2 raised to power x. Now we open the bracket, so we have 5 multiplied by x. We have 2 raised to power 5x minus 5 times 3 will give us 15. So multiply by, we open here 3 times x will give us 2 raised to power 3x. 3 times 4 we add plus 12 is equals to, here we can now apply the second row of indices and write this is 2, 6 minus x. From there we apply the first row of indices to the left hand side, so this side. So we have 2, we add the indices, so it is 5x minus 15 plus 3x plus 12 is equals to 2 raised to power 6 minus x. Now 5x, we add the like terms, 5x and 3x we add, you get 8x minus 15 plus 12, you get minus 3 is equals to 2, 6 minus x. Now since the base is now common, it means the indices are the same, and therefore we can write 8x minus 3 is equals to 6 minus x. So we have now, we bring x to this side. So when you bring x to this side, it will becomes positive, and you take 3 to the other side, it becomes positive also. Therefore we have 8x plus x is equals to 6 plus 3. So this is equals to 9x is equals to 9. We divide both sides by 9, so we divide by 9, so 9 divided by 9 you get 1, 9 divided by 9 you get 1, so it implies our x is equals to 1. So that is the answer to that question. So in this question we are supposed to find x. So what we do, we try to establish a common base. So 8 is the same as 2 to power 3. This is into bracket x plus 2 multiplied by 2 x plus 2 is equals to 32 is the same as 3, is the same as 2 to power 5. Is the same as 2 to power 5. We open the brackets here, so you have 2, 3 multiplied by x is 3x. 3 multiplied by 2 we add, it is 6, plus multiplied by 2 x plus 2 is equals to 2 to power 5. Now from there we have we apply the first row of indices, so we have 2. Now we have 2, we add the indices, this and that, so we have 3x plus 6 plus x plus 2 is equals to 2 to power 5. Now here we add the right terms, so 3x plus x is 4x, so we have 2 to power 4x. 6 plus 2 will be 8, so plus 8 is equals to 2 to power 5. 2 to power 5. Now we have a common base, therefore we equate the indices, so we say 4x plus 8 is equals to 5. We take 8 to the other side, so we have 8 to the other side, so we will have 4x is equals to 5 minus 8 implying 4x is equals to minus 3, and therefore we divide both sides by 4. We divide both sides by 4. So 4 divided by 4 is 1. So implying our x is equals to minus 3 over 4. So that is how you work out that question. So in this question, okay, we apply the rules of indices. So we can write 49 as factors of 7. So 49 is the same as 7 squared. We tie this into bracket, x plus 1 plus 7 2x is equals to 350. So you open the bracket here, we have 7 to power 2x, and 2 times 1 is 2, so plus 2 plus 7 2x is equals to 350. So from there we can separate this. Since it is addition here, we cannot apply the rules of indices. So we separate here and write this as 7 2x multiplied by 7 squared plus 7 to power 2x is equals to 350. So we realize that here we have 7 to power 2x is common, so we factor it out. So we have 7 2x into bracket. Here we'll be left with 7 squared. Here we'll be left with 1, so we have 1 is equals to 350. So here 7 squared is 49 plus 1 is 50, so we have 7 2x multiplied by 50 is equals to 350. So divide both sides by 50. Divide by 50. So 50 divided by 50, you get 1. 350 divided by 50, you get 7. So it means that now we can say that 7x, 7 to power 2x is the same as 7 to power 1. So it means, since we have now the same base, it means 2x, the indices are the same. So 2x is equals to 1, implying when we divide both sides by 2, then we divide by 2, 2 divided by 2, you get 1. So our x is equals to 1 over 2, or 0.5. 0.5. So that is the answer to that question. So question number 6, we are supposed to solve for x in the equation 5 to power 2x minus 1 is equals to 12. So this one we will not be able to apply the rules of indices, but we will apply the logarithmic rules, which says we have the log of x raised to power y is equals to y logarithm of x. So we can apply this rule to be able to assist us solve for x. So we have we get the logarithm for both sides. So we have the log of 5 2x minus 1 is equals to the logarithm of 12 to power x. Now applying this rule, you say 2x minus 1 into bracket, the logarithm of 5 is the same as x, the logarithm of 12. Here we open the bracket, so we have 2x multiplied by log x will be 2x log 5. Here minus 1 multiplied by log 5 will be minus log 5 is equals to x, the logarithm of 12. We bring, this is logarithm of 5. We bring log 12 to the left hand side and log 5 to the right hand side. So you have, here we have 2x, the logarithm of 5, minus x, the logarithm of 12, is equals to logarithm of 5. From there, we factor out x. So we have x into bracket. We have x. So we have x into bracket. Here we will be left with 2 log 5. 2 log 5. Minus, here we will be left with log 12 is equals to log 5. So we can now divide both sides by 2 log 5 minus log 12. So our x will be x is equals to log 5 divided by 2 log 5 minus log 5. So using a mathematical table or a calculator, you should be able to get your x, which is equals to x is 2.19. So that is how you work out that question. So in this question, we are going to find x. So we can write 4 factors of 2. So we say 4 is the same as 2 squared, close the bracket, at index x plus 1 is equals to 32 is the same as 2 to power 5. So we open the brackets. Here we have 2 multiplied by x, you get 2x. 2 multiplied by 1, we get 2 is equals to 2 to power 5. Now we have a common index, and therefore we have a common base, and therefore the indices are the same. So we say 2x plus 2 is equals to 5. We take 2 to the other side, to the right hand side. So we have 2x is equals to 5 minus 2. 5 minus 2, we get it is equals to 3. So 2x is equals to 3. Divide both sides by 2. When you divide both sides by 2, 2 divided by 2, you get 1. So our x is equals to 3 over 2, or 1.5. And that is the answer to that question.